So not last week, but on Tuesday, you guys did one of two kinds of ears. You either did a red and a white, or you did a purple and a yellow ear. And so I'm going to look at the purple and the yellow, and I'm going to look at the two possibilities because it worked the same way for the red and the white. So the same thing happened. So you counted your corn kernels, and you came really close to either getting 75-25 or 50-50, right? Okay. Jesse, tell me how yours came out.
Do you want the exact number?
Mm-hmm. Percentages, please.
77.
Okay, so like 77-23 is really close. Sorry. To 75-25. So in that case, we would say that we would expect this to be about 75-25. But we have to work backwards. We're going to work backwards to figure out our Punnett square. So we're starting with the offspring and working backwards to figure out what the parents have. So now, which trait did we determine was recessive? So which trait, the purple or the yellow, which one was recessive?
Yellow.
Yellow is recessive. So if 25% are yellow, how many squares out of 4 is that going to be? That's going to be 1. So, and the only way to get the yellow is going to be to have what? The only way to get the yellow phenotype is to be able to have what genotype? 2 of the yellow genes. Now notice, guys, I used capital letters because when we started, we didn't know which one was recessive. So we really couldn't use a lowercase letter because we didn't even know. When you guys start working the Punnett squares, I don't care what symbol you use as long as you know what it means. So if you know that the recessive trait, you got to have 2 of the same genes. I don't care if you use stars, circles, triangles. I don't care what you use. I like using all capital letters because especially when we used to do other types of inheritance like codominance and incomplete, it was just easier. So if you're going to like work your way backwards. So we're starting here with the yellow and the yellow in this square. What has to be up here at the top for us to have a Y in this box? What's this going to have to be? So, what's going to have to be up here for a Y to be in this box? A Y. All right. And then what's going to have to be over here? The Y. So I just did it backwards. Now, I think if you guys got a 75-25, I told you that both of your parents were purple. So, what has to be on the other 2 boxes for the parents' genes? They're going to have to be P's, right? And so we just pair those up. And then in this box here, over and down, we're going to have PP. In this box over here, over and down, we're going to have PY. Over and down, we're still going to have PY. And so you end up with a Punnett square. We have 25% that are homozygous dominant, 50% that are heterozygous dominant, and 25% that are homozygous recessive. Now, who had a 50-50 ear? Who had an ear that was about 50-50? All right. What did your numbers come out to be?
24 and 23. Yeah. Down one row, then we multiply by 4.
24 and 23?
Yeah.
Okay. So you only had... Oh, okay. So that's about 50. This is about half and half. So, I think I told you in that case that that one parent was purple and one was yellow. Now, in this case, how many squares would we have to have all yellow genes in order to make that work? 3? Why 3?
Because purple is dominant, so we would have So if you have 2 yellows on one side and then 1 yellow on top, then the whole right side would be.
Oh, okay. You mean you mean up here. You mean up here at the top. I see what you're saying. But I'm talking about for the offspring, how many squares have to be YY?
2.
2. So I'm just going to do that. I'm going to put YY and YY. And as he said, we're going to have 3 squares with Y's on them. And this one up here is going to be a P. So both of the offspring that are purple are heterozygous. Because one parent's yellow, and then your other parent has to be heterozygous to be able to have those genes. Because you never get both genes from the same parent. You get one gene from one parent, one gene from the other. And so you have to look basically at what's there. So we're going to do something else today with your tasting data. And so I'm going to give you guys a little bit of instruction on what a pedigree is. And then I'm going to have you do one. So you guys tested your parents and you tested yourself to see if you could taste the bitter chemical or not. So the PTC paper, that tests to see if you have a dominant gene for tasting bitter tastes. You know your phenotype, but you don't know your genotype. And that's what we're going to figure out today. So that's why I had you test your parents, so you could figure out your genotype. So we're going to do something today called a pedigree, and I've got some instructions for this, but first I want to show you how the symbols work, and then I'll turn you loose on it. So a pedigree is kind of it's almost like a family tree of traits. When squares in a pedigree represent males, and circles represent females, and I'm talking about, I'm referring to biological sex here. So if someone is a biological male or female, these are the symbols we use. Now, if the symbols are shaded, that means they have the trait. They are affected with the trait, whatever it is. Pedigrees do not tell us if the trait is dominant or recessive. So we don't know that. And you have to figure that out by interpreting the pedigree, which we're going to practice later. Now, if a male and a female are married or mating, we don't just use pedigrees with humans. They're often used with dogs and cattle, whatever it is that you're looking at the lineage of. So, a circle and a square joined with a line is married or mating. So, they are having children. Now, if you put a line down from that, you can add the children. So this couple has a girl and a boy. Now, if one of those children marries, like let's say the daughter here gets married, we're going to add her husband, and then they have a daughter. So you guys can kind of see how this works. You just keep adding on. Notice that the husband is in no way connected to the parents other than through her. And so in that case, we're looking at, we don't want the line down from the parents to him because he's not their child. So that is how we use a pedigree. One other thing I want to show you, if one of the individuals is deceased, like here, let's say the grandfather of this girl here is deceased, then you put a line through him. And you guys will see that on your instruction sheet for doing this. So what we're going to do today, I'm going to have you use your data and make a pedigree for your parents, showing you. You can also include brothers and sisters if you tested brothers or sisters. But then you and your partner are going to pretend to have 2 children. So the way we're going to do this, you're going to get data from somebody else, and you're going to set up a Punnett square as if you were having a child or having 2 children. And we're going to use something called a D4, which is a 4-sided die. And there's two ways these can work. When you roll the number is either going to be at the top, right side up. Some of them. Excuse me. Sorry about that. The number is going to be right side up, whichever way. It doesn't matter. All the other numbers will be upside down, so you're going to read the one that's right side up. And so I've set up the Punnett squares to where each square has a different number. So you're going to roll to see which possible genotype your child has, because this is all based on probability. So you have 4 possibilities, just like in the Punnett square. So this goes like 1, 2, 3, and 4. So you're going to roll to see what biological sex your child has, if it's male or female. And it explains in the sheet how to do that. And then you're going to roll to see which genotype your child gets. Does it make sense? And then we're going to set up a pedigree using that information. Any questions?